So turbulent flow is different than laminar flow. And the reason why we can't use the previous equations um, to solve for the friction heat loss term is because of that principle, that turbulent flow is different than laminar flow. And a major reason why turbulent flow is different than laminar flow is because the faster moving fluid, which is at the center of the tube, and the slower moving fluid, which is near the wall, increases the shear stress over that which would exist in laminar flow. So there's extra stress in turbulent flow, and this extra stress is called a Reynolds stress. And because of that, the actual friction heat loss in turbulent flow is greater than that predicted by even a Pazuli's equation. In the so that's very important to understand. And for turbulent flow, that fancy F term is proportional to the average velocity squared divided by the diameter. It can also be proportional to delta x, or x delta as I'm writing it. Delta x multiplied by average velocity squared over d. Same thing. Now we're going to introduce another term here, the friction factor. We have the fancy F again, friction heat per pound mass equal to 2F friction factor. Multiplied by delta x multiplied by v squared divided by d is equal to 4F delta x over d. Multiplied by v squared over 2 You can solve for F here. You can solve for F. If you solve for F, you get that fancy F divided by 4. Let's see. That should be delta x over d. This term is going to go at the bottom too. So v squared over 2. I'm trying to do this on my head here. Yeah, that should be right. So this is what the friction factor um, is equal to. Now, there are two different types of friction factors. Usually the one that we use in chemical engineering is going to be considered or referred to as the fanning uh, friction factor. Fanning being spelled out F-A-N-N-I-N-G, fanning. And this is exactly what we had defined just a few seconds ago. Rewind it. That's what this is. And it's for chemical engineering disciplines. This is not to be confused with the Darcy friction factor. And the difference between the Darcy and the fanning is that the Darcy is 4 times as great. There is no 4 at the bottom of the equation as there is with the fanning factor. Fanning, there is a 4. For the Darcy, there is not a 4. And this is also known as the Darcy-Weisbach friction factor. And this is commonly used in civil or mechanical engineering. So they are not the same. If you see a Darcy friction factor, you want to make it fanning, it's not that difficult to just multiply by 4. It's really not. If you see a fanning, you want to convert it to a Darcy, all you do is divide by 4. It's very simple, not hard, but important to note that there are differences. And Poisson's equation can be rewritten as the friction factor equaling 16 over Reynolds number. And this is the fanning. This is the fanning. Most of the equations from now on that are using a fanning factor, or that are using a friction factor, will be the fanning friction factor. This is coming from a chemical engineer's book, fluid mechanics book for chemical engineers. So we will be dealing with a fanning friction factor more often than with a Darcy friction factors. But if you're studying fluid mechanics, from a civil or mechanical, maybe even aerospace engineering discipline, you might be using the Darcy. Consult your book or ask your teacher or ask a classmate if you are not sure. This factor is equal to a number, a very tiny number, 0.001375 multiplied by this exciting expression, 1 plus 20,000 epsilon over d plus 10 to the 6th over r over Reynolds number to the 1/3. This is important to know. To find problems, to find reading values of friction factors, you need to know that this problem, this fanning friction factor, is equal to 0.01375 multiplied by the expression 1 plus 20,000 epsilon over the diameter plus 10 over Reynolds number, 10 to the 6 over Reynolds number, this expression being raised to the 1/3 power. Epsilon in this case is absolute roughness. Okay, so there are 6 parameters of flow, usually represented in some sort of chart. Could be called a Moody chart. And these factors include pipe diameter, average velocity, fluid density, fluid viscosity, pipe roughness, and the friction heating per unit mass. This equation here, Q, is the volumetric flow rate. It's equal to pi over 4 d squared diameter multiplied by the average velocity. And this will give us our volumetric flow rate. For long horizontal constant diameter pipes, Bernoulli's equation can be rearranged into this: negative delta P over delta X is equal to rho over delta X multiplied by that fancy F, which is frictional heat per unit mass, equal to fluid density multiplied by 4 fanning friction factor over diameter multiplied by velocity squared over 2. I've approached the time limit for this video, so I will see you in the next video.